part of the class anyway. So, all right. So, um, we are starting chapter 4, as you guys can see. Chapter 4 is control volumes. And so, we need to start here and kind of define what a control volume is, right? So the first one, conservation of mass for a control volume. So if anyone's ever heard of like we've already talked about conservation of energy, right? Conservation of energy essentially just means that energy is being accounted for, right? Either by heat transfer, by work, or the energy level in the fluid, right? It's being accounted for. There's nothing leaving that we don't know about, right? Mass is the same way. So mass is conserved in a similar way. Essentially, that mass going in must equal mass going out, right? Because mass just doesn't, it doesn't just disappear, right? Like it is going somewhere. Now you guys might be like, well, it could get stuck in the tube or something, right? Okay, yes, right. But then mass going in wouldn't exactly mean mass going out, but like, you get the point, right? That in a flowing system, mass in must equal mass out, and that's essentially what this is saying right here. So it says developing the mass rate balance. So the time rate of change of mass contained within the control volume. So this is delta M. So essentially the change of mass, right, has to be equal to the mass in minus the mass out, right? So this is basically what this is in words. This right here is what it means. So the change of the mass of the control volume is equal to the mass in minus the mass out. Is anybody too concerned with how does that make sense? I think that probably makes sense. So now you can also sum it. So over down here they summarize it, and this could be delta M. So let's say, for example, you have 2 inputs to the system. So let me open EpicPen. This is a very similar one. This is something you'll probably see in this class. Like let's say it was, something like this, right? So obviously in this system there are 1, 2, and then they meet up at 3, right? So there's 2 inputs to the system and 1 exit, right? So you have to account that in this MI, right? The mass in is 1 and 2, and mass exiting is 1 and 3, or is 3. So how you would write this is that mass 1 plus mass 2 has to be equal to mass 3, right? Does that make sense? And by the way, because we're now doing control volumes, remember, because they are all with respect to time, you have to add a dot to the top of M, right? So it's a mass flow rate. It is no longer just a specified 4 pounds or something, a total mass. This is mass flow rate. So this pretty much makes sense. Logically, it follows, right? That mass going in must equal mass going out. And so that's what you're going to be doing a lot for this chapter, is things like that. So let me get rid of that. Let's move down. All right. So then we have evaluating the mass flow rate. So I don't know if we really, this is just rearrangement of the equation. So evaluating a mass flow rate. So what this is that you guys are going to have to find ways to find mass flow rate. And so we have to figure out a way how to do that. So right here, an expression for the mass flow rate M dot of the matter entering or exiting a control volume can be obtained in terms of local properties by considering a small quantity of matter flowing with velocity v across an incremental area dA in a time interval delta t as shown in this figure. So that was just a lot of calculus, mumbo jumbo, right? But it's going to make a little more sense in a second, so just give it a minute. It says, since the portion of that control volume boundary through which mass flows is not necessarily at rest, the velocity shown in the figure is understood to be the velocity relative to the area. The velocity can be resolved into components normal and tangent to the plane containing dA. In the following development, Vn denotes the component of the relative velocity normal to dA in the direction of flow. The volume of the matter crossing dA during the time interval, delta t, shown in figure 4.2, is an oblique cylinder with a volume equal to the product of its area, of its base, dA, and its altitude, Vn, delta t. Multiplying by the density P gives the amount of mass that crosses dA in time, delta t. So this right here, I'm sort of laughing because they essentially have you know, made this really complicated for not really a whole lot of gain. And so, essentially what this is, guys, like this is what you need to know, is that mass flow rate is equal to rho v. So this is velocity, or this is rho va, I'm pretty sure is what it is. So let me see the units. So rho is density units. So essentially, you just need them to get them to cancel, right? So that's like the that's essentially what it comes down to, right? I'm pretty sure it's rho va, and I think v is velocity. So I'm going to denote that with a line here, right? But you can also see this in other terms, because velocity times area gets you volume, which is a volumetric flow rate, which is in terms of meters cubed per second, right? So this would be in meters per second, right? So this would be meters cubed per second. So you could just see these two combined, and you would just get rho times v dot gets you that. So you have to understand that there is like a definition inside of each other. So I'll write that again just to be sure. But essentially what this is saying is that was a lot of things to say. What I just said is that the mass flow rate is equal to that. It's equal to this right here. But not exactly that, because you don't want to see the dAs. It just is equal to rho VA. So mass equal to rho V, so this is that, a velocity, rho VA. And then down here, VA is also equal to V dot, which is a volumetric flow rate. And this right here is something that you will have to use, because a lot of the questions in this class have to do with, it'll tell you a volumetric flow rate, and it'll say the water, or then you'll have to find the, you find the velocity, and you have a volumetric flow rate, and it'll ask you what the area is, right? It'll ask you what the area of the pipe is. And so you have to know that inside of velocity, or inside of volumetric flow rate, there is an area, and you have to be able to pull the area out and be able to work with that. So you have to be careful. A lot of people forget that this is a relationship, and so they end up messing up the question. And also, one other thing to consider is that density is the inverse of specific volume. So you can also have the equation written like this, divided by little v, right? So understand that there's a lot of different ways this equation can be written based on how these definitions work. So you can use specific volume, and by the way, a lot of times you will, because remember we use the tables, right? So you will have a way to find specific volume in all of these cases. So specific volume is very helpful. So you get specific volume, and then you can have the big V over over little v, right? You can have velocity times area over little v. You could have velocity area times rho. You could have big V times rho. There's a lot of ways that this equation can present itself. So make sure that you understand that there's all these combinations work, right? So let me go ahead and get rid of that as we move along. All right. So then we have forms of the mass rate balance. Oh, they're actually about to show everything I did. That's funny. So it says one-dimensional flow form of the mass rate balance. So this right here is the, I guess, the conditions that it has to apply under. The flow is normal to the boundary at locations where mass enters or exits the control volume. All intensive properties, including velocity, density, are uniform with position over each inlet and exit area through which matter flows, right? So essentially these are some assumptions we're making. We're assuming that inside of this pipe, right? So let's say we draw this pipe. We're assuming that essentially there is no, they're uniform. Essentially all the properties as we go through this are uniform. Because I don't know if you guys have taken fluids or, maybe higher level heat transfer classes, but a lot of times at the boundary layer, which is the edge of the pipe, flow is not the same. There's like a velocity gradient there, and we're just assuming that doesn't exist. There is no flow there. We're assuming that it's all going the same speed, right? This is our assumptions. All right, and that means it's one-dimensional. So right here, this is, when the flow is one-dimensional, this equation becomes this. So this is the first one I showed you, which is mass flow rate is equal to density times area times velocity. Then we have the next one, which is in terms of specific volume. They switched out density for specific volume like I did. So mass flow rate is equal to area times velocity over specific volume. And then there's another form, I'm sure. Nope, okay, oh yeah, it's volumetric flow rate. So then you have the last one. And then it says AV in equation 4.4 is the volumetric flow rate. The volumetric flow rate is expressed in units of meters cubed per second or feet cubed per second. And this right here, they represent it the same way as mass flow rate. So if you recall, the change in mass of the control volume, so they've written this essentially. So the change to the mass of the control volume is equal to AVI over VI minus AV exit over V exit. So this is inlet, outlet, right? Inlet, outlet, inlet, outlet. And so essentially what you're going to have to do is you're going to summarize how many inlets we have and how many outlets we have, and that will tell you your total mass flow rate at the end, right? All right. So then we have steady state form of the mass rate balance. So steady state is what we are going to assume everything in this class is. So everyone do listen up here. We are going to assume that steady state applies for basically all of our questions. And what steady state means is that all properties are unchanging with time. And so what that means for you is that essentially we assume that if mass flow rate, so let's say mass 1 at M0, let's say mass flow rate at 0 seconds is 100, right? We are also saying mass flow rate at n seconds, 1,000, a million, whatever you want to put in there, is also equal to 100, right? So we are assuming that this is unchanging. Think of it like a pond, right? When there's nothing going on, it's very uniform, right? It's the exact same thing. Time doesn't affect it unless something happens in it, right? That's what we're assuming this is. We're assuming it is unchanging throughout time. So the mass in equals the mass out regardless of the time added, okay? All right. So then we have, let me see, if any of this stuff is really that important. Yeah, okay, I'll read it. So it says, actually I'll go back up here. So it says, for a control volume at steady state, the identity of the matter within the control volume changes continuously, but the total amount present at any instant remains constant. So dm CV delta T is equal to 0. So the change in the mass of the control volume is equal to 0. And equation 4.2 reduces to what I just circled. It says that is the total incoming and outgoing rates must be equal. Note that equality of total incoming and outgoing rates of mass flow does not necessarily imply that a control volume is at steady state. Although the total amount of mass within the control volume at any instant would be constant, other properties such as temperature and pressure might vary with time, which is true. This is something that you'll see when you take, or in the last chapter of this class and the first chapter and basically every chapter of the next class, is that because the mass flow rate is the same for the whole system, it does not mean that pressure and temperature won't change, because you do all of your analysis on power cycles using that thought. You go, oh, okay, so for this, for this turbine, over here at this turbine, it comes in at 600 degrees Celsius or something, and it's at this mass flow rate. And then later, when you get towards into liquid phase, you'll say, oh, it's not 600 degrees anymore, clearly, right? And it's also not the same. It's the same mass flow rate. So essentially what it's saying is do not confuse the two. Just because mass flow rate is the same doesn't mean all the other properties stay the same, because they do not, and they won't. We are just talking about mass. We are not talking about anything else. All right. So then we have the integral form of the mass rate balance. I think that these are not really, I'm not really worried about this. So we can move on from that. Yeah, it's integral forms are always confusing to people, and I don't think they help very much. And all they did was here is explain the mass flux, which anything, if you ever hear the word flux added to it, it means it's something over area. So like a heat flux is your heat transfer divided by the area it's going over. And that's what this is. It's the mass flux. So it's flow rate per unit area. All right, so then we have applications of the mass rate balance. So we will do this question here in a second. And you guys, I want you to really pay attention because this will be a good setup for how you do all these other ones. And it might take a little minute. So it says, for a control volume at steady state, the conditions of the mass within the control volume and at the boundary do not vary with time. The mass flow rates are also constant with time. Example 4.1 illustrates an application of a steady state form of the mass rate balance to control volume enclosing a mixing chamber called a feed water heater. Oh man. Yep, feed water heaters are components of vapor power systems in chapter 8, which is what I just talked about. Open feed water heaters and closed feed water heaters are something you'll see in chapter 8, which is not in this class. It'll be the next class. It'll be the first chapter of the next one. All right. So let's look at this one really fast. Yeah, this actually is. Wow, it's really funny. All right, let's go look at paint. Let's get a good example of how this stuff works. All right. You know, really to sell it and, you know, knock it home. So we got to do what we always do, right? We have to figure out what we know and what we don't. So the first part, I'll put this off to the side and turn down this a little bit. So it says a feed water heater operating at steady state. So steady state means obviously mass I equals, or not mass I. So the mass 1 is equal to mass 2, which is equal to mass 3, right? So essentially what that means is that mass does not change. The mass flow rate does not change. It says has 2 inlets and 1 exit. So obviously the 2 inlets are right here on the chart, as you guys can see. So you have 1 here and 1 here, and we have some conditions with both of them, right? That we need to work on. So we got to break these up. So let's talk about inlet 1. What do we know about inlet 1? So inlet 1, it says water vapor enters at P1 is 7 bar. So we have pressure 1 is 7 bar. One is just bar. And we have T1 is 200 C, right? And it says with a mass flow rate, so they've given us M1 is equal to 40 kilograms a second. Very helpful. And now let's talk about the mass flow rate of 2, or the inlet of 2. So inlet 2. And by the way, you can also read these down here. So if you don't see it here, I'm trying to get it out of your way, but you can read it down there on the chart too. They've just listed it. So then we have, at inlet 2, liquid water at pressure 2 as 7 bar, and T2 is equal to 40 C, enters through an area, so we have given A2 of 25 cm cube, right? So they've given us liquid water here. And so what that means is that this is, what liquid water usually means is that it's saturated liquid. But we're actually going to go look at this in a second. I'm going to check these properties and see where it actually lies. And then it says saturated liquid. Okay, so this isn't saturated liquid, or this is subcooled then. This has to be subcooled, and I'll explain why I know that in a second. And then let's do inlet 3. So inlet 3 here. So inlet 3 or exit 3, or exit, but we'll just say 3, right? So we have exit, and it's just determined by 3, right? There's 3 states. 1 inlet, second is another inlet, and third is an exit. So, and then it says saturated liquid exit, so they have given us X3 is equal to 0. So it says saturated liquid exits at 7 bar. So they've given us a quality. And then we have P3 is equal to 7 bar, and exits at 3 with a volumetric flow rate. So they've given us V dot. So how am I going to do this one? I don't know. So I'll just do vol 3. Can you guys, vol 3, I'm saying that's the volumetric flow rate at 3. 6 meters cubed per second. Okay, And so what you are having to find here, you are having to find the mass flow rate at inlet 2 and at the exit in kilograms and the velocity at inlet 2. So there's a lot of things we got to do here. So there's a lot of stuff going on. So I'm going to put this over here on the side. So what we need to do is we need to find out. I got to get this kind of out of the way though. Pull this back up. Okay. So what our first step is that we have to figure out some things, right? We have to figure out the things necessary to solve each state, right? I think that's fairly not complicated. So we have to figure out here, right? We have to figure out inlet 2's velocity. We also need to figure out the mass flow rate at inlet 2 and exiting. So does anybody have any ideas of how we would start something like this? I know it's a lot of things to look at. Anybody have any thoughts? Anyone? Doesn't appear like anyone has any thoughts today. That is okay. It is a new subject. I don't expect anyone to have any thoughts. But do pay attention. So what we need to do first, yeah, it is Monday. I agree with you. I agree. So what we have to do is let's write our very base equation here, right? So let me put this down here. So let's start with this. So what do we know? We know that the mass flow rate of 1 plus the mass flow rate of 2 has to be equal to the mass flow rate of 3, right? Does everybody agree with that assessment? And the reason why is because we have one inlet here, another inlet here, and then the third is an exit, right? So the addition of mass of 1 and the mass of 2 have to be equal to 3, right? We're not losing any mass anywhere else. Okay? So how can we rewrite this? So we can rewrite this in a different way here. So this might be something helpful for us, is that M2 is then equal to M3 minus M1, right? Because we know M1, you guys would agree. We already have M1, it's up here. And so you can rewrite this in a different way, right? You can have M3 over here, M2 minus it, but we already know that one, right? We already know that. So this is a rewrite. So M2 is equal to M3 minus M1. And that makes sense, right? Because the exiting mass minus one of the inlet mass has to be equal to the other one. So hold on to this equation really fast. Hold on to that. Okay? Now, let's go look at, so how we have now picked this out is that we now have to find M2. That is what we're looking for. But to do that, we have to know M3. So can we find M3? So we can. And the reason why we can is that if you look at M3 here, we were given a volumetric flow rate. So let me go work at this. I'll put this down here. So let's do state 3. So we were given a volumetric flow rate. So let's look at that equation, the mass equation. So M3 is equal to vol3 times density, right? So we'll just call it rho. Rho 3. Or we can also use specific volume, right? Everyone is following with that. We can use either density or specific volume. So divided by V3. Okay? So with that being said, we now need to find specific volume 3, right? To easily solve for the mass. Like it's right here. All we need to have is V3. And so we need to go to the tables and go look up the things that we know. So we know X3 is equal to 0, and we know pressure 3 is 7 bar. That is enough. That is enough that we can find it. Yes, Drew. Anything? Anything you got going for me? So, I'm going to go ahead and go to this really fast, and we will look at this. So we go look at the tables, and we go to 7 bar, which is right here, and we slide across to the specific volume of liquid, because we are saturated liquid, so the specific volume is 0.001108. So I will write that out. So using table, no, I have done it again, ladies and gentlemen. So I'll write this out again. So vol 3 divided by V3 is equal to N3, right? And so we go to the table. So table A3, I think this one is. Yep, table A3. And you find V3 is equal to 0.00110. Let me see, 0.01180, right? And this is meters cubed per kilogram, right? So this is what we have right here. And so now that we know that, we can immediately solve for the specific, or the mass flow rate, right? Pretty straightforward. We solve for the mass flow rate. The mass flow rate, does anybody have a calculator handy? If not, that's okay. I will do it on screen. But essentially, we have M3 is then equal to, you just have to do the volumetric flow rate, which is 0.06 meters cubed per second, divided by 0.0011080. And if you do that math real quick, somebody, if not, like I said, I will do it. So we have 0.06 divided by, you have 541 kilograms a second. I will go and make sure, but I'm pretty sure you're right. You have 541. Did I type that in wrong? I have 54.1.
That's what I got, was 54.1.
Oh, okay. So did you, Tanner, did you type it in right? Make sure you did. You're off. I don't know if I'm off by a factor of 10. Probably not. Well, that's not super confident, but that's okay. So that right there is the mass flow rate of 3, right? And because we now know the mass flow rate of 1, and we know the mass flow rate of 3, we can find the mass flow rate of 2, right? Just simply because of this relationship we typed in earlier, which is the mass flow rate of 2 has to be equal to the difference of the other 2. So let's go right here. So mass 2 is equal to 54.1 minus 40, which was, I think, the first one, right? Yes, 40. And so it is 14.1 kilograms a second, right? That is the mass flow rate of 2, and we have just solved one part of this, right? Pretty straightforward. We have solved the mass flow rate of state 2, which I will go ahead and circle that for. Actually, let's see what the highlighter tool looks like. Where is the highlighter tool? Is this it? No, it's an oil brush. Yeah, whatever. Doesn't even matter. I'll just circle it. So, all right. So that is one of our answers. So now we have to do the next one. So that was only one part, right? The other part of this is that we had to find the mass flow rate. Wait a minute. Oh, so we already found the mass flow rate at the exit too. That was another part. I didn't think that was a part of the question. So yeah, this is also a part as well. So we have 2 parts of the question done. And now we need to find the last one, which is the velocity at inlet 2. Okay? So that's the last part. Velocity at inlet 2. And so this is, once again, just another very simple manipulation of the equations at hand. So let's go ahead and write this one out. So let's go state 2. So we know that this equation applies for this one too. M2 is equal to rho 2 times, so it's rho VA. So yeah, V2 times A, right? Does that make sense where I've gotten this from? Essentially, once again, density of 2 times velocity of 2 times the area of 2 is equal to the mass flow rate. And since we know mass flow rate, we can maneuver and bring over everything else that isn't that. So how the equation ends up turning out is you have mass flow rate 2 divided by rho 2, although if we want to use specific volumes, which I think we should because the tables give us specific volumes, so this turns into specific volume down here. So I'll actually just rewrite the equation just a little bit here. So what it ends up turning into is that this one is specific volume is down here, little v2. And then we end up multiplying back. So trying to make this look nice. What this ends up looking like is the following. It ends up looking like M2 times little v2 divided by A2 is equal to v2, right? So we just really manipulated that first equation. That's what a lot of this is, guys, is that these questions, a lot of them are just manipulating this rho VA equation and finding what you need. That's all it is. And if you don't know something in the equation, like let's say we're trying to find mass 2 here, you have to find the other things, right? So that's all this is just manipulating this equation. It's a little different from the previous chapter. This one's it's a lot more manipulating of the equations. So now that we know that this is how we have to solve it, right? We know this is how it has to be solved. We have to know everything here. Well, we can go through. Do we know M2? We do know M2, right? We found it up here. It's 14.1. Do we know specific volume of 2? The answer to that is no. We do not know that yet. But we can find it, right? Because, if you recall from the very beginning, we were given a temperature of 40 and a pressure of 7 bar. Now, I said earlier that this was a subcooled liquid, and I am fairly certain that it is. And the reason why I know that. So let's go look at 7 bar. Yeah, if you go look at 7 bar, we're at 40 degrees. We're way lower than this, right? And the reason how I knew that it was going to have to be that way was because our exit, so our exit gave it away. So because our exit was a saturated liquid, so if we look at, I'm going to draw the little TS diagram, or not TS, I'll draw a little PV diagram, right? This is just like a little trick for my mental. So if I know that state 3, so let's draw a pressure 3 is right here, right? So this is pressure 7, so this is 7 bar. Right, on this line. If I know that the exit here is x equals 0, it's saturated liquid, and I know that the very first one, if you guys remember, the very first temperature, because this is how these look, our very first temperature was 200, right? So it was way over here and superheated. To get state, crap, I drew that wrong. I'm supposed to put this is supposed to be a 3. So to get state 3 to be a saturated liquid, state 2 couldn't be in here. It couldn't be past 3 because heat transfer doesn't work that way, right? It can't ever be, you can't ever go lower than the lowest range or higher than the highest range of two things being added together. And so if the exit is right on this line, I know that state 2 can't be in front of it. So state 2 had to be colder than saturated liquid. And since it's colder than saturated liquid, remember saturated liquid is the border between subcooled and saturated. So that means it had to be subcooled. Immediately off the bat, I already knew state 2 was subcooled. Just that's my little like check for heat transfer, right? Just to give you a little bit of thought process into how I did it immediately. And some of you might have thought that as well immediately. But just to start thinking about these things. So, since we know it's subcooled, we now have to look it up at its temperature, though. Remember that, guys, is that if we are approximating values, we have to look them up at the temperature, not the pressure. So, we must go to the temperature table and go find 40 degrees, which is right here. And let's get our specific volume value of 0.00. So, I'll pull this up here really quick. So, V2 is equal to 0.001078, right? Meters cube per kilogram. Okay, so we now have that. Now we have to find the last one, right? And so we now have mass 2 and we now have V2. We now need to know the area 2. And some of you are like, well, wait a minute, they gave us the area 2. But did they, though? Anybody see a problem with what they've given us?
Well, that's just for the exit.
No, they gave us the inlet area for area inlet 2. So we need to find area 2, and they're not the same. And so the problem is, and Tanner is correct here, is that essentially they gave us in centimeters cubed, and our units here at the bottom are all in meters cubed. So we have meters cubed, we have kilograms per second. We need to get it to meters cubed, or meters squared, right, for this to cancel properly. So we need to get this right here to meters cubed, or meters squared, which, what is this, divided by 100? Right? Am I correct? Make sure someone's fact-checking me here. I know it's political season, so fact-check me away. Pretty sure it's 0.25, right? Area would be around 10,000. Remember, these are centimeters. Divide by 100. We have to turn it to meters. So this is centimeters, right? So this is smaller than a meter. So this is, okay, that's fine. I'm pretty sure it's 0.25. Because, I don't know if anyone wants to actually like see this on the screen, but what is it? You have 25 cm squared. Actually, wait a minute, you might be right here. No, wait a minute, I don't think you're right. Never mind, maybe I'm just dumb. So then, so what is it? It's point something cm squared is equal to, wait a minute, what am I doing here?
When you take 1 meter squared divided by 100 centimeters squared, the centimeters squared canceled out, divide 25 by 100.
Yeah, I'm confusing myself with the English units. Like English units, you have to do like a bunch of weird stuff on the bottom, and it's like you'll find out that you have to like divide by a bunch of weird stuff. But yeah, you're right. It's just I started second guessing myself, and 0.25 is what I got. Is that everyone's figured? Fairly certain that's what it was. So. Yeah. Don't worry, guys. I do the exact same things as you. I second guess the shit out of myself all the time. So, 0.25 meters squared, right, is what I'm going to call it. So, divide by 100, right? So, 0.25 meters squared gets you that. And then if you just throw this into the equation right here, so you would get V2 is equal to, let me do this, 14.1 times, what was the other one? This is 0.001. Someone go ahead and start typing this in, by the way. I would appreciate it. Divided by 0.25. And this is meters squared. And And I'll put the units here as well for this one, meters cubed per kilogram. And so if you do these units out, the kilograms cancel. You're left with 1 meter at the top, and you have a meter per second. So that it makes sense, right? Velocity should be in meters per second. And so does anybody have this number? Because I don't have, I really need to charge this calculator. It's been sitting next to me for like a week and a half, and I just haven't charged it.
I got 0.05684. I rounded up to the 4 meters a second.
So you said point what?
0.05684 meters a second.
No, so what's his name was right. Tanner was correct here. Is that, remember, so for area, we have to multiply it times each other. So essentially it ends up being we're off by a factor of I think 100. So I just looked at it. So essentially the area, it's 10 to the 4th centimeter square is 1 meter squared. So we divided by 100 when we should have divided by 10 to the 4th. So that was our problem. And so if you do that, you end up getting, so here I'll do that again. So let me do this, 0.25, 25 divided by, and then let's do it now. So I'll actually, 14.1, I'm going to multiply it out on my calculator really fast. Yeah, units are hard, guys. So essentially what you end up with is that it should be, we were off by a factor of, like I said, 10 to squared. So it should have ended up being 5.6 something, or 5.7 is how if you round up. And this is how it is here. I'll show you. Like I said, I'm also a units loser as well. So 25 centimeters squared. And then you have 10 to the 4th, because remember, since it's an area and not a just a length, you have to do 10 to the 4th, because this is 2 times that essentially gets you towards the 1 meter squared. So it's 25 centimeters squared. This is 10 to the 4th centimeters squared. These go away, and if you divide by 10 to the 4th, you end up getting it to meters squared. Or how they did it, since they already did it on the bottom, they multiplied by 10 to the 4th, because they put this on the bottom already, just like the answer. And you should get 5.6 something. I think I got 5.68, something like that. So 5.68 meters per second. Yeah, per second. Yeah, have to be careful. Definitely have to be careful. Like I said, I'll make the mistakes too. So, let me see this. So yeah, that's our other answer as well. Yeah, that's what I was gonna do. I was trying to think about right at the beginning. I was like, but then I thought about it. I was like, man, like why do I have to multiply by 2 times that? I was like, if it's just a meter, right? I was like, you can just cancel that right away. It's exactly how I thought about it too. But gotta be smart, a little bit smarter. I'm gonna bonk myself on the head. So right here we have all the answers that we were looking for: mass flow rate of 3, the mass flow rate of 2, and the volume, or the velocity of 2. So we found everything that we needed to find here. These are how a lot of these questions end up going though. They'll give you things like a turbine, and there'll be like 2 inlets, 1 outlet turbine, and they give you all this same stuff. So this type of question is exactly the same. You will be getting things like this, and you have to just find other things. And there are some times where they'll ask you for, like, this one's really weird. So really fast, this is like just to prepare you, I think, for the homework. There are some times where they'll ask you what the radius is, or the diameter of the pipe. And so if they do that, what you have to do is in the following equation, so in that, this, like I said, just to prepare you, because they do ask for this. So in that mass, so M, let's say M1 is equal to VA over little v, right? VA over little v. So if you do this right here, and they ask you for the diameter, what you have to do is you have to break up. You have to go M1 is equal to V. Then you have to do pi in here. So pi times d squared, or yeah, pi d squared over 4, right? So then you have to do that, and then you have to solve for diameter. So do be careful. You have to then break apart the equation even further if they ask you for that, which they will, by the way. Your homework is going to ask you for that, so please remember this. So don't be too confused when they ask you for diameter of the pipe, because this is what they mean to do. They mean that you have to break area into its components and then solve for diameter through that. All right. So are there any other questions not besides this, like about like grading the class? I don't know. We're kind of at the you know, the first exam mark. You guys survived, although I don't know how scarred you are from it. But let me shut the recording down.